Now we're going to talk about properties of the probability density function. So the property we learned most recently is that if I take the area under the curve from a to b, that gives me the probability of my variable being between a and b. So the probability density function itself is not a probability, but it does have to be greater than or equal to 0, because if it weren't greater than or equal to 0, then we would have area below the curve and a negative probability, and that just doesn't make sense. So that's our first property of the probability density function. The second one has to do with how much area there is under the curve. So if I take the improper integral from negative infinity to positive infinity of my probability density function, I can interpret that as the probability that the number resulting from my random trial is between negative infinity and infinity. And this should always be the case. So that needs to be a 1. So the second property of a probability density function is that if I take the area under the curve over the entire real line, that needs to be equal to 1. So a few things to remember. Number 1, a probability density function is not the same as a probability. In fact, if we have a continuous random variable, and continuous random variables are the kinds that we're sort of most concerned with, this bit here is always going to be 0. Whereas our probability density function should not be 0 everywhere, because in fact it should have a positive area under the curve. Why don't you pause the video for a second and think about these next two true or falses. The second true or false kind of expands upon the first one. A probability function is not a probability. They actually can be greater than 1, just as long as the total area under the curve is not greater than 1. So probability density functions can be greater than 1. Capital F of x is what we use for a cumulative distribution function. This is a probability. This is the probability that my random variable comes back less than or equal to the number x. So this one is true. If you're having a hard time with these, the things to remember is capital F is a probability, lowercase f is not. Now that we have some properties of a probability density function, we can figure out which types of functions are probability density functions. So here's an example. F of x is a times e to the minus absolute value of x. Let's first sketch a little bit what this is going to look like. E to the negative x would look something like this, and that absolute value means that it's mirrored across the x-axis. If a were negative, this would be below the x-axis, but one of the properties of probability density functions that we just learned is that they have to be greater than or equal to 0 all the time. So that tells us our constant also needs to be greater than or equal to 0. The other property that we learned of a probability density function is that the area under the curve over the entire real line needs to be 1. So that's how we're going to be able to solve for a. So what we need to do now is we need to find the area underneath this curve. We can do that with an integral. Remember the definition of an absolute value. If x is positive, that absolute value doesn't change it. If x is negative, that absolute value changes the sign. In order to have to keep from doing two separate integrals with positive x and negative x, I'm going to take advantage of the fact that I have a symmetric function. The right-hand side and the left-hand side look exactly the same. So I'm going to first rewrite this as 2 times the integral from, let's say, 0 to infinity, a e to the minus x dx. So I'm taking this area on the left of the curve, and instead of computing it separately, I'm saying, well, that's the same as the area on the right. So I'm computing the area on the right and multiplying it by 2. I can factor out that a because it's just a constant. And because now I am only dealing with positive values of x, the absolute value no longer changes my function. So this is just e to the negative x. The way we deal with improper integrals is by replacing the problematic bound, in this case it's the upper bound, with a limit. So I'm going to take the limit as b goes to infinity of this function. Now I can anti-differentiate. The antiderivative of e to the negative x is negative e to the negative x, and I'm evaluating it from 0 to b. So this looks like minus e to the minus b minus e to the minus 0. E to the minus 0, of course, is 1. E to the negative b, well, we've actually already sketched that function. Here's e to the negative x, and I can see that as x gets real big, this function gets really small. So I have a negative exponent, that means I'm dividing by something. So this limit here goes to 0. So what did I just compute? I just computed the area under this curve, the curve of my probability density function, over the entire length of the real line. This needs to be equal to 1. That is the property that we're using. So this tells me a needs to be 1/2. And that finishes the problem. If a is 1/2, this is a probability density function. If a is anything else, it no longer makes sense as a probability density function. Now we know that if a is 1/2, this function is a probability density function, so we can find its cumulative distribution function. Before we do, I'm just going to sketch this again. Let's call this the t-axis. If I want to know the cumulative distribution function at some value x, remember that's the probability that our variable ends up being less than or equal to x, this is going to be the area for everything to the left of x of my probability density function. Now, because we have that absolute value in there, this is going to behave differently based on whether x is positive or negative. Let's first think about negative values of x. If x is negative, the cumulative distribution function of x is going to correspond to this area underneath the curve, which I can figure out with a straightforward improper integral. If I'm only concerned with negative values of x, the absolute value of t is negative t. A negative is a positive. Because it's an improper integral, I need to replace my problem bound with a limit. I know that this exponent is going to be negative, and I am indeed dealing with negative numbers. So this is just going to be e to the t. And if I refer back to my sketch here, I can see, yes, this is just, looks like e to the x. Of course, that shouldn't be 0 in the upper bound. That should be x. This is straightforward enough. As a goes to negative infinity, e to the power a goes to 0. So this whole thing looks like 1/2 times e to the x. So this tells me my probability density function in the case that the number I'm plugging into it is less than or equal to 0. Just to again remind you what that means, this means f of 0 is 1/2 e to the 0. It means f of -1 is 1/2 e to the -1, and f of -2 is 1/2 e to the -2, but we have not yet figured out, for example, f of 1. Now, let's figure out what's going on for positive values of x. I still want to know the area under the curve. I still want to know the area under the curve from -infinity to x of my probability density function. But because x is piecewise defined, I have to be a little bit more careful. When my x is positive and I want to know the area under the curve, I need to figure out these two bits separately. So this bit on the left, my function just looks a little bit different from how my function looks on the right. But I can figure that out easily enough from what I've got. I know this is 1/2 e to the 0. So this is 1/2. And then I just need to add in this blue section here. When x is positive, the absolute value of x is just x. So for this integral, I can just drop the absolute value of t, because I'm only considering positive values of t. And now I evaluate this integral. It's not even improper anymore. So now between these two pieces, I can write down the entire cumulative distribution function. It's going to have to be piecewise. And here it is. Here is my cumulative distribution function.